Okay, so now we're going to go into gory detail. So first we'll do alpha. Alpha. Okay, now remember, what's an alpha? It's a helium-4. Right? So it's a Mack truck compared to an electron, right? Okay, so here's just an example. Here's an example. Let's talk about radon-222. All right? So this is a typical alpha emitter. So we have radon-222, and it has Z86. It's nice when you write it like that, right? Then you don't have to look it up. All right? Now, remember, it's an alpha emitter, so it's going to spit out an alpha. Well, when it spits out an alpha, it's going to leave something behind, right? So we don't know what's going to be, we have to figure out what's going to be left behind. So this thing, it leaves behind something. It spits out an alpha. What's an alpha? Again, helium-4. And then it spits out energy as well. It emits energy. All right? So that's an example of an alpha decay. Now, what our job is to figure out what the X is. Okay, now it's easy, right? It's easy. Okay, remember, this is the number of protons, right? And what did we learn about charge back in electricity days? We learned that charge is conserved. Well, if we start off with 86 protons, we got rid of 2 of them. What do we have left? 84. So this is 84, okay? And this is the number of nucleons. You can't, that's also conserved. So we started out with 222 nucleons. We got rid of 4. What do we end up with? 218. Okay, so now what you got to do? Now you got to look up in your chart, which I'll give you on a test. Don't worry about it. So what's Z equals 84? It's polonium. So you got to look that up, right? You got to look this up. So you just look up the Z, right? Just the Z is 84. It's polonium. So there it is. It's supposed to be a PO there, polonium. It's not P0, it's PO, polonium, okay? So there it is, okay? There it is. That's alpha decay. Okay, now they use kind of funny terms here. So this is the, this is the before, this is the after. So what they call it, this is the parent, and this is the daughter. I don't know why they don't use sons, but they don't, right? So parent, daughter. Okay, so you start off with the parent, so X, A, Z, all right? And then what happens? So this is the before, you have some parent. So the alpha particle, a fast helium nucleus, carries away most of the energy. So the daughter has 2 fewer protons, right? 2 fewer protons, and 4 fewer nucleons. 4 fewer nucleons because of this, right? And it has a small recoil. So basically, this is just, all right, compared to this, I call the alpha particle a Mack truck. Well, that's compared to the beta. But what is this relative to this? Like if this is uranium or something, right? 238 protons or something like that. I mean, 238 protons and nucleons. So compared to a big uranium nucleus, this is really tiny. So this just goes off really, really fast. Just kind of just moves a little bit, to conserve momentum. So that's all there is to it. Not a big deal. But here's something that's interesting. So you notice that energy is emitted, right? Energy is emitted. What does relativity say? Well, therefore, the mass of the radon has to be greater than the mass of the polonium plus the helium, right? In other words, right, this mass has to be greater than that mass because the missing mass becomes energy, okay? So this is a spontaneous decay. It doesn't require energy, it just happens. So spontaneous decay, all right, spontaneous decay. And you look it up, so the energy, for whatever reason they call it Q, right, the energy released in one of these radioactive decays. So 0.006 U, which is 5.59 million electron volts. Million electron volts. So again, that's why it's dangerous, right? Okay, so you can wipe out molecular bonds and so forth and so on. Okay, so that's alpha. Okay, beta. All right, now, beta, people learned a lot with beta because what they thought was true initially turned out to be wrong, turned out to be incorrect. So, people they figured out alpha, and they just figured out that beta would be kind of the same, So let's do it. Okay, so we'll do beta minus, okay? So a beta emitter is phosphorus 32. So let's just write it down. So 32P, so that's phosphorus 32. Everybody knows it's a beta emitter. So phosphorus 32. So again, it spits out, so it leaves behind something we call X, because we don't know what it is, right? And it spits out an electron. Now, what's an electron? So you write an electron, right? Remember, this is the nucleon number, Z plus N. This is A, Z plus N. Number of protons plus number of neutrons. Well, how many protons and neutrons does an electron have? 0, right? Okay, what's the charge? This is the proton number, or you can just say this is the charge. 15 protons is plus 15. What's the charge of an electron? -1. Okay? All right. So P32 becomes whatever this thing is, we figure out. Here's the electron plus energy. All right? Okay. Now, so what's X? Well, 32 plus 0, plus 0 is what? 32, right? All right? You start with 32 nucleons. You're not getting rid of any, so you have to have 32. Now here you have a plus 15. Here you have a -1. What does that have to be? 16. All right? It's good old addition, isn't it awesome? So you look it up. What has Z equals 16? Okay, all right? Sulfur. Okay, so that's beta minus. You could also have beta plus, where this would be a +1, so you have to subtract, right? So it's beta minus and beta plus. Okay, awesome. So you think you're done, right? Big deal, You start off with some isotope, call it X, A, Z. You spit out an electron. The A stays the same, and this increases by 1 because this is negative, right? Right? So that doesn't change. This increases by 1. Big deal. So that's it, right? Okay, so that's what everybody thought, and everything was great. But then some other people did more experiments. Now, this is called a two-body decay. It's a two-body decay because, you start off with P32, right? And then, you spit out the electron, and you spit out this, whatever this is, sulfur, I think. Okay? Two-body decay. This thing decays into two bodies, right? Two-body decay. All right. Now, people that studied two-body decay, that's two-body decay, right? Now, people that study that, and, if this is at rest, what has to be conserved? Momentum, right? Momentum. And also, you can conserve kinetic energy. So, you write down momentum conservation, you write down energy conservation, and you just look at the kinetic energy. You get this, right? So don't forget, Q is the energy that's released, right? Okay, so you have two particles. This is the kinetic energy of one particle. This is the kinetic energy of another particle. Now notice, this is just going to be some number, right? Some unique energy. This is going to be some unique energy, right? So then you're not going to have different choices, or you're not going to have a variety or a range of energies. This is going to be the energy for number 1, number 2. Big deal, right? No range of energies. So let's just graph K1, for example. So if you do the experiment, and you measure the kinetic energy of particle number 1, you just see, you get a peak at this one particular value of energy, okay? And that's what everybody knew. Big deal. Everybody knows that for two-particle decays, You get a certain value of K1, you get a certain value of K2. Just depends on the masses and the energy released, All right. Awesome. Now, when you have 3 particle decays or 4 particle decays, you know, it's like, you don't have something like this. There's gobs and gobs of different combinations of final energies, okay? They're not just this one or this one, all right? The energy can be divided up into many, many, many different ways, okay? Depending on the masses and the directions and all sorts of stuff. But again, all we're talking about is this decay here, which is obviously a 2-body decay, so they used to think, all right? So they expected to see this, you know? That's what they expected to see. Well, you know, you don't ever believe anything until you do the experiment, right? So they did the experiment. Oh, my gosh. This is what they saw. They're supposed to see this. If it's 2-body decay, they saw that. Whoa. All right. So what's going on? How would you explain it? I mean, you know, where did this come from? That came from momentum conservation and energy conservation. You see this? Now look at people back then, they were firmly convinced this was a 2-body decay because they never detected any other object being emitted. So they thought, what's going on here? This is a 2-body decay, and they're seeing this. So how would you react? Well, how would you answer that question? Well, gee, you know, I mean, maybe energy and momentum aren't conserved. Oh my gosh, that's heresy, right? Or maybe it's a 3-body decay. But wait a second, they never detected a 3rd body, you know, another particle. Okay, so oh my gosh, right? All right, so it's either a 3-body decay, but they never found the 3rd body, right? Or energy and momentum aren't conserved, and ooh, that doesn't sound good. Okay, what else is wrong? What else is wrong? We didn't talk about this a lot, but each of these bodies, okay, so something's wrong, right? Also, every one of these particles has spin, which is angular momentum. Now, we talked about angular momentum conservation. Angular momentum should be conserved. Well, this one has a spin or angular momentum of 1. This, right, we're doing this P32, okay? This has 1, this has a half. Is angular momentum conserved? No! Well, what do you mean, no? Well, what's going on? So again, what's going on? Is angular momentum not conserved, or maybe it's a 3-body decay? But they didn't find the 3rd body. Okay, oh my gosh, oh my gosh. Okay, so 1930, there was a guy named Bohr. Remember Bohr from quantum mechanics? So in 1930, Bohr said, well, you know, we looked for the 3rd body, and we didn't find it, so it has to be a 2-body decay. But what can I say? It appears that angular momentum, regular momentum, energy are not conserved in these reactions. Man, it took a lot of guts to say something crazy like that, you know. So there's another guy named Pauli, Wolfgang Pauli. Wolfgang Pauli. He said, Bohr, you're nuts. He said, come on, we've never found a situation where momentum, angular momentum, energy have not been conserved. This has to be a 3-body decay. We just haven't found a 3rd body or the 3rd object. Now, he didn't just say that. He actually made a prediction for the 3rd object, all right? So, just think of it like a ghost particle because they didn't find it, you know? So the third particle, call it the ghost particle, right? This is what Pauli figured out. It had to have mass approximately equal to 0. Oh boy, right? Oh boy. It had to have no charge, and it had to have spin equals to a half, right? It has to have spin equals to a half, right? Because you know, because anyway, work it out and it does. All right. Okay. Well, actually, negative a half, right? Because then it would kill that, and then it would be conserved. Okay. Now, so people, I'm just exaggerating. So what would you say? Something like this. Oh, I get it. So it's like has no mass. So it's kind of like nothing, but yet it's spinning. Oh, Sounds crazy, right? Okay. He didn't stop there. He said that there has to be another nuclear force, which became known as the weak force, that governs this ghost particle. Okay? Now, so this is like I said, 1930-ish, around there. This particle, this ghost particle, was given a name by a guy named Fermi. He called it a neutrino. Now, Fermi was from Italy. What is ino? That means a small, right? So like a small neutral one. Huh? Small neutral one. Okay, well, this neutrino was finally discovered in 1953. 1953. That's 23 years after Bohr, gave his opinion on the whole thing, right? And luckily, when it was discovered, these two guys were alive. So, everybody was alive. All right? So it's called a neutrino. So what everybody thought was a two-body decay is actually a three-body decay. That's important because now we know there are these things called neutrinos, and the sun emits neutrinos. I mean, there's a lot of physics with neutrinos. So yeah, this was a crucial discovery of a neutrino because we wouldn't understand how the sun shines without neutrinos. I mean, there's just tons of science that started making sense with the discovery of the neutrino. So here's beta decay. So we start off with this guy. So there's the parent, there's the daughter, there's the electron. It turns out it's an anti-neutrino. Don't worry about it, all right? Just think of it as a neutrino. Okay, if only the electron and the daughter nucleus are measured, energy and momentum appear not to be conserved. The missing energy and momentum are carried away by the undetected anti-neutrino. So this is beta minus. Beta plus has a neutrino. Don't worry about the just neutrino. Okay, so there you go. Very nice. Now, wait a minute. You should think about this. Look at this carefully. Remember, we're talking about nuclear physics. Nuclear physics. What's in the nucleus? Proton and neutron, right? Look at this. Something should be smacking you in the face. You should be thinking, wait a second, this is nuts. What should you notice? Neutrons, protons. Where in the world does the electron come from? Right? We're talking about a decay of a nucleus. There's no electron there, right? So what's going on? Where's that come from? Well, the electron actually comes from the decay of the neutron. Okay? All right? So that's what's really, this is a P32 decay, but this is what's really going on. So what's really going on is that one of these neutrons is becoming a proton. So the neutron becomes a proton plus an electron plus the antineutrino plus energy. So that's where the electron comes from. The electron comes from the decay of the neutron. Now, let's go back to E equals mc squared. In order for this process to occur, what must be true about the masses of the neutron and the proton? You should be able to answer this without even thinking. So pause your video and figure it out. And E equals mc squared. Okay, there's energy, right? There's energy and all this other stuff being created. So the mass of this has to be greater than the mass of that, right? Because some of that missing mass forms all this other stuff. E equals mc squared. Okay? So the mass of the neutron is bigger than the mass of the proton. How much bigger? Not very much. Okay, so the mass of the neutron, 939.57 MeV per c squared. Mass of the proton, 938.28 MeV per c squared. Now here's what's kind of funny about it. You look in the cover, the first page or something of the book, inside cover or something like that. It says, look at what it says. Mass of the proton and mass of the neutron. So basically, to this number of sig figs, they're equal, right? Right? The masses of the neutron and the proton are equal. But they're not. Remember, they're not, right? They're not, okay? And they can't be because you wouldn't have this if they were equal, agree? And so they're not equal, even so it says it in the inside cover of the book. They're close, but they're not equal, okay? So don't forget that. All right. Oh, here's a question for you. Oh, yeah. Okay, here's a question for you. So I-31 is used a lot for thyroid cancer. So I-31 is a beta emitter. So when I-31 beta decays, what's the daughter? So I-31 is a parent. What's the daughter? So use what you learned here and figure it out. So pause your video and figure it out. Okay, hopefully you have an answer. Let's check it. Okay, so we have 131.53 iodine goes to some mystery plus E0 -1 plus antineutrino, which I don't care about, plus energy. Okay, so what is this mystery guy? What does the daughter have to be? Well, 53 minus 1 has to be 54. 131, 0 has to be 131. But you have to look it up, right? You got to look it up. In your table of isotopes or whatever, you look it up, and it's xenon. Ha! So I can use a Z. I'm an X. Okay? So xenon, 131.54. Okay. Last, we had alphas. We had betas where we learned about neutrinos. Now we have gammas. Gamma's not too exciting. All right, this is how you write it. So this is just mean it's a high energy, excited nucleus. It spits out the gamma, and it's just a regular nucleus. I mean, remember, gamma has no charge or anything like that. It has no neutrons or protons. So there's, that's all that's going on, right? So again, high energy nucleus becomes a low energy nucleus, unstable, stable, spits out a gamma. But don't forget, I mean, gammas are the ones that are used in cancer therapy, so they're incredibly important. Now, oftentimes, a particular isotope will be a gamma, will be an alpha, beta, and a gamma emitter, all three. So let's look at this guy, see? So it's an alpha emitter, a beta emitter, and a gamma emitter. So boy, that's dangerous, right? That's dangerous. And that's one more? I guess no. So that's plutonium. Plutonium is incredibly dangerous, incredibly toxic. If it accumulates in the bone marrow, that's where it goes, then it emits all three types of radiation. It's lots of danger, lots of harm to the human body. Okay, let's quit. All right, good.